Okay, now we're recording. So our first type of reactor is a plug flow reactor. And I guess just for comprehensiveness, in case you're watching the podcast, this was the key idea sheet. I'm not going to repeat all that. You'll just have to pause the YouTube. And now we're going to keep moving. Hopefully you all wrote all that down. So PFR stands for plug flow reactor. And it is going to be represented, like I said, by a tube. The tube is supposed to be symmetric. It's not really symmetric. One of my professors taught me how to draw tubes like this, and I always thanked him for it, because it's such a neat way to draw. Isn't that a nice tube? Oh, completely unrelated. I found glow-in-the-dark hair scrunchies over the weekend. It's like I didn't know what life was prior to that. So it's just a tube. There's nothing inside the tube. There's nothing fancy that you're missing if you think, well, what's inside that tube? There's nothing inside that tube. Normally, the way that we initiate a reaction inside a plug flow reactor is one of two ways. Either there is catalyst on the walls, like you have on that catalytic converter going around, or we heat it up, right? So one region of the tube is cold, the reaction is not occurring there, and then it enters something that got hot. Maybe we have a Bunsen burner or something like that, but there are no moving parts, there's no mystery inside a plug flow reactor, it's just a tube. A little bit of the nomenclature that we use in terms of molar flow rates. For this class, everything is F sub I. So I'm going to put a circle next to, or a zero, because that's what's coming in. Usually you'll see that this has some kind of units of something like amount per time. So here I've said moles per second. And then the inlet usually requires also some temperature and some pressure. Similarly, what comes out the other side is a molar flow rate F sub I, which is again something like a mole per second. At some new temperature and pressure. Oops, I forgot my subscripts. These are T0 and P0 over here, because those are inlet conditions. So T0, P0. If we know all molar flow rates and all temperatures and pressures, we know everything there is to know about what this reactor is doing. We can do the entire system in terms of concentration, but we won't get to that until we finish the material balance. In order to do a material balance on something like this, we're going to start with a little control volume. So I'm going to do my control volume in pink. And entering this control volume is one stream. It's some molar flow rate. I'm going to subscript it as I. We don't know what that molar flow rate is. And leaving it, we're just going to focus on a single species at the moment. It also comes out. We're going to add another subscript to that in a moment. This little element that we're dealing with is tiny, but it does have some volume associated with it. It's delta V. So remember, it's a cylinder in most cases. We've taken a small slice of that cylinder. So I've kind of drawn it as a rectangle here, so it does have some length associated with it. The other dimension is that it goes all the way around the cylinder, so it's like a squat little cylinder. In terms of nomenclature, the stuff that's entering is coming in at some volume V. What does that volume V mean? That means that reactant, whatever species I is, has encountered up to that point some volume V of the reactor. It has traveled that far into the reactor. If you felt more comfortable, you could redo this entire analysis in terms of length. You could say it's gone so and so many meters down the reactor. Volume is usually the one that we do in case the reactor is not a cylinder. For example, if it's one of those triangles that's floating around, then volume's a little bit easier. When it exits this little control volume, it has now experienced that same volume V plus the tiny little element of volume delta V. Right? It has passed through the reactor a tiny bit. We're looking at a very tiny slice of this reactor. Therefore, we're going to denote the entering amount as V sub I, or sorry, F sub I evaluated at V And the one coming out is F sub I evaluated at V plus delta V. So there's some coming in at whatever location V is, and then there's a little bit more coming out at delta V. Within that reactor, within this control volume in here, since I can't actually draw that, there is a reaction going on at rate R sub I. Right? If there's no reaction, then you don't have a very good reactor. Remember, the units on R sub I were amount per volume per time. So if we want to know how much was consumed in that tiny little volume, we would multiply R sub I by our delta V, because delta V represents the volume of that tiny little chunk. Our good friend, the material balance, says that accumulation is in minus out plus generation. Technically, there's a consumption in there, but we're not going to worry about consumption because that's just negative generation. All of the reactors that we're going to deal with will have no accumulation, which means they are running at steady state. Right, so if I sit there with a camera or some sort of a probe and I never move it from that particular location, for our reactors, everything's always going to look the same. That particular location will always have a particular molar composition, a particular temperature, and a particular pressure. It's never changing. It does change as we go down the reactor, but in terms of time, it never changes. The amount that's coming in is just F. Sorry, was that a question or a squeak? So you get paranoid when you're teaching long enough that any sort of a noise you pay attention to. So the amount coming in is however much F sub I is evaluated at V, and the amount coming out is F sub I evaluated at V plus delta V. And then the amount that we generate, what color did I use? Red, green? Is R sub I times whatever your volume element is. This term, notice if we multiply that volume by this looks like a rate again, right? It's a mole per second. Just like these are mole per second and that's a mole per second. So our units are matching up. Okay, so far. Actually, I'm going to write that explicitly over here because we're going to encounter a different version in a moment. The units on R sub I are something like amount per volume per time. Because we're going to introduce another version of I in a moment that has slightly different units. So if I take this expression, and I'm going to rearrange it a little bit, I'm going to leave R sub I on the right-hand side. I'm going to move these two over there, and then I'm going to divide everything by delta V. Have you seen a term that looks like V plus something evaluated at V plus delta V minus something evaluated at V divided by delta V? It looks like a derivative, right? If I move that around and I have that term and I let delta V go to a very tiny element, basically let it go to 0, we will get a derivative. So if I rearrange that, I would have something like F sub I evaluated at V plus delta V minus F sub I evaluated at V divided by delta V. I'm going to draw a really long equal sign here, because if we let delta V go to 0, in that limit we now get a derivative dFi dV is equal to R sub I. So this represents our material balance on a plug flow reactor. And keep in mind that this is at steady state. Things look more annoying than we're going to try to deal with if you're not at steady state. This also needs one additional element, which is what? An initial condition. So now our initial condition is not what happened to the reactants at some known time. It's typically what is happening to the, or what kind of reactants do we have when they enter our reactor. So when the volume is 0, that means you are at the inlet of the reactor. The reaction, or the reactants have not experienced any volume within the reactor. So typically you will have initial conditions that look like F sub I evaluated at V is equal to 0, which will typically be denoted as Fi0 as the initial condition. That's not a particularly remarkable initial condition. You experienced it an awful lot in CENG 100. That's just whatever happens to be going into the reactor. Those are your initial conditions. We aren't going to get to the energy balance for these, I think, until Friday or possibly next week. But there will be additional initial conditions for both temperature and a new one for pressure that we'll have to deal with. Okay, so that's it. That's the only material balance. But that should look pretty similar, right? That looks similar to the material balance we had for a batch reactor, except a batch reactor, instead of an F, we had an N, and instead of a V, we had a T. But the math here to solve it looks almost identical, except now we're talking about volume changes instead of time changes. Personally, I would keep using N for all of them, but if you use too many N's, it gets confusing, because then you don't know which N you're talking about. We'll get to the other V in a moment. Any questions on anything I did here to get that equation? I'm not going to ask you to derive any of these, but it's important to know where they came from. It's a straightforward application of our material balance. No? All right, cool. So let's look at the other version, which is the packed bed reactor. The packed bed reactor is usually abbreviated as PBR. So this is packed bed reactor. By the way, both of your projects are based on packed bed reactors, so this is relevant. And we're going to start off with the same sketch that we saw before, with these awesome tube ends. And we've still got material coming in. Nothing has changed about this terminology. It's still Fi0, T0, and P0. And everything coming out is the same as it was for a plug flow reactor. So some amount of material, F sub I, evaluated at some temperature and pressure. The only difference is what we interpret to be inside of our control volume. Where's my tube with catalyst spheres? Has it made its way all the way around? You got it? Thank you. So remember, the whole tube is filled with some sort of a catalyst, which we're going to assume is spheres for now, because all I can draw up here are spheres. Spheres are not the only kinds of catalysts that we get. In fact, they're usually not particularly good because they pack a little too tight and they inhibit the gas flow. But nevertheless, we can derive everything based on spheres because all we're going to do is draw it. We're never actually going to assume the shape is a sphere. That's just what we're drawing. So as the gas enters on one side, it's going to encounter some spheres. When it gets to some element, right, what is that element? We're just going to draw a pair of dashed lines that represent a segment of these spheres. They're just going to cut right through the spheres. So if I draw this again, it's going to look exactly the same as it did before for a plug flow reactor, except now we have to keep in mind that there are actually spheres inside of here. So I'm going to draw little circles inside here. Got to get them all, or the math won't work. Happy little spheres. Right, there are some spheres in there. The spheres are everywhere. I just haven't drawn them everywhere because that would be too much drawing. All of the terminology is also the same, except now instead of talking about the volume over which we have gone in our little reactor, we're going to talk about the weight of the spheres. And this is one time where I don't know how this trend got started, but if I'm talking about the weight of spheres in there, I really mean the mass of spheres. Weight and mass aren't the same thing, which if you either already took fluids or you're about to take fluids, it would be really frustrating if a book used weight wrong, and the book uses weight incorrectly here. We're talking about the mass of spheres that's in there. So when you see weight being thrown around, weight is always going to have units of mass, like kilograms or pounds. It's never going to have pound force or Newton, even though that's what weight is. So keep in mind that weight really means mass in this particular class. We've drawn a little chunk of it here, the amount of weight of catalyst in there is delta W. And just like before, if the gases have entered our control volume here, they have experienced some weight W of catalyst up until that point. So they've passed over all the spheres to here, right up in front of that control volume, which represents some volume W, or sorry, some weight W. By the time it leaves our little control volume, it has then experienced weight plus delta W. This, by the way, anytime that I give you a homework or an exam problem that says the kinetics for so-and-so were derived in the following way, or derived from the following source. This is a really convenient way for you to determine what the kinetics are, which is to fill up everything in this region. Just put non-reactive catalyst particles, and then give yourself a tiny, tiny little slice of reactive particles and then non-reactive particles. The reason being you don't have to deal with gradients anymore. The temperature doesn't change and the pressure doesn't change. So this little control volume element is useful not just for the math that we're about to do, but also to actually figure out what kinetics are. And I am blanking on the name of that reactor, so I will randomly yell it out once I figure out what it is. Nevertheless, we have some amount of F sub I entering at W, and some amount of F sub I exiting at W plus delta W. The rate that occurs inside here is a little bit different from the rate we saw before, but only in terms of units. So just as we saw before, there is a reaction that goes on inside here, which I'm going to draw. Did that show up a little bit? Yeah, kind of. Gray and green don't mix very well. There is still a rate inside here, R sub I, but because packed bed reactors typically care about the amount of catalyst that you put in here, the weight of catalyst, the units that we usually use on this R sub I are slightly different, so we put a prime on it. The units that we're dealing with, R sub I prime, is usually equal to an amount per mass of catalyst per time. This is directly proportional to the other rate that we saw before. If we know how much catalyst we can fit inside this tube, if we know, I dumped so-and-so many grams of spheres and that takes up such and such an amount of volume, we can directly relate this R prime to the previous R prime that we used. If we multiply by mass of catalyst per volume of bed, this should look like a density, but it's a slightly unusual density. Usually when we talk about density, we would, for example, if you want the density of water, it's the mass of water per unit volume of water, right? When we talk about densities, it's the mass of something over the volume of that same something, whatever it is. The density that we're dealing with here is a little bit different because the catalyst doesn't make up the entire volume. Right, there are open spaces inside there for the gas to pass through. If there were no open space, that would be a solid block of copper and you wouldn't be able to get any flow through it. So this particular term has it's still a density, but we usually put a subscript on it, which is the density of the bed. So we would abbreviate this as rho sub B. Your book uses rho sub B. You will also see commonly rho sub lowercase b, and you will see rho sub bed. Or you could see rho sub bed. Right? All the same thing. It's talking about how much catalyst can I pack inside that bed. This is the term that changes if you don't have spheres. Right? Different shapes will have different what are called packing factors, which means I can fit more or less mass of catalyst of a particular shape inside of my reactor. So the catalyst might always be copper, right? Copper always has a particular density. It doesn't change no matter what the shape is. But if I make that copper into a sphere, I might get something like, 60% of that space is taken up by spheres, and therefore my bed density would be something different. If I change it and use cubes, I can fit more or less cubes in there. If I use a different size of sphere, I can fit more or less inside there. If I use, triangles, triangles or something funny like that. This term can be different depending on the shape of the catalyst. So this is not a density in the same kind of density terms that we've seen before. Eventually, when you do your project, you'll see exactly how this relates to the density that you've observed in previous classes. But if you take those two and multiply them together, you will get the previous R. Right? Because the previous R had units of amount per volume of bed per time. So the two are directly related. And it's pretty rare, actually, that we have to move back and forth between the two. But it is possible that you will have to move back and forth between the two. Usually the times that you have to move back and forth between the two are if you write the rate laws in the same way that we've always written them. Some people will report their rate laws with rate coefficients on a per volume basis, and you'll need to know what the density is of your catalyst in order to get it to a per mass basis. But it really depends on the problem statement. The easiest way to figure out whether you need to do that conversion is just check your units, right? If your rate law is given as per volume of bed, and you're talking about the weight of a catalyst, then you'll probably need that term. If it doesn't, then you're on the volumetric term. If you're using a packed bed reactor, you will almost always need to use this term. If you're using a plug flow reactor, you don't have a choice. It's always this, because you've never put anything into a plug flow reactor. Yeah?
So you have written there a mass catalyst in those equations.
Yes.
If you had a, like you were saying, you'll use a sphere because oftentimes you'll coat the sphere in a catalyst. Would you only include the mass of the catalyst on that sphere, or the entirety of the sphere, including non-catalyst parts?
If you wanted to calculate the density of the bed,
yes,
then you would need the mass of the whole chunk,
okay,
right? So these spheres are a copper shell over a polymer interior. I would need to put that entire sphere on a balance, and whatever that number is what this is.
okay,
Not the mass of the copper shell.
okay.
So catalyst here means the whole particle that you dump inside it, including any substrates that are on it. There is an intermediate tube somewhere in between packed bed and plug flow. If you only fill this up to about halfway and pass your reactants up through it at a rate fast enough that those things start to lift up and sort of circulate around, that's called a fluidized bed, which is somewhere in between the two. But usually you'll pick whichever one of these looks more like that reactor and just use that version. So these forms that we're going to learn here can be extended to other types of reactors. I'm not going to go into a fluidized bed, but we do have fluidized beds. When you get to the 176 lab, we have a couple of fluidized beds in there. If you ever get the opportunity to run your hand through a fluidized bed, it's really crazy. I dig it. It's unrelated to the topics that we're about to talk about. Like I said, if you're in chemical engineering for long enough, these are the things that become exciting. So if we do that same material balance, accumulation is equal to, I don't know if those are pity laughs or what, but I'm going to go with it. In minus out plus generation again. I'm going to skip a couple of steps because this is rewriting everything in almost exactly the same way, except we're changing this subscript from V's to W's. Right, if I rearrange all of these, I will end up with a new derivative, which is dFi dW is equal to R sub I prime. This, I've used a different color, is the material balance, but it's on a packed bed reactor. And again, this is its steady state. So I'll let you do the algebra here if you want to rearrange it, but you'll end up with roughly the same answer as what we saw before. This one, just like the other one, needs an initial condition. So normally we would say F sub I at W equals 0 is equal to whatever Fi 0 is. This is our initial condition. So again, as with the plug flow reactor, when we said V is equal to 0, that just means what is it at the entry point of the reactor. When we say W is equal to 0, that just means when the gas came in right here at the bottom and it hasn't encountered any weight of catalyst, what's the composition? It's whatever the inlet happens to be. If any time you do need to use a conversion between weight and volume, keep in mind that the weight of catalyst in the bed is equal to the density of the bed times the volume of the bed. Should you need to move back and forth, you can always do it. If somebody tells you, here's the particular bed density that we're dealing with, tell me what the volume is, and you only know how to calculate the weight, you can then get the volume on the equation like this. Not often that we have to go back and forth, but I am pointing out that these are directly related to one another. Any questions on our two material balances so far? All right, let me briefly summarize just so that before we introduce a little bit more terminology. So if we have one reaction, we have some forms, and if we have more than one reaction, we have some forms. We've already seen batch. Now we have two more, which is PFR, which is plug float reactor, and packed bed reactor. So the batch reaction for one reaction looked like dxa over dt was equal to r sub a over na naught. And for a multiple reaction, we saw that we didn't really use that form very much. We just talked about moles. So as moles of I with respect to time was equal to r sub I. We can always use the multi-reaction form for the single reaction, right? There's no reason we can't interchange these. It's just we can't go the other way around. There's not really a good way to take the one reaction form in terms of conversion and use it for more than one reaction. If you use the plug flow reactor, the definition of conversion has not changed, except now in terms of N, you have F, right? The difference between what came in and what came out over what came in is X. I'm going to state that again here, but I just want, while these differentials are in your mind, I want to show you how similar these are. So now you have dxa, what are we on? Plug flow? Yeah. With respect to V, is equal to r sub a over f sub a naught. And the general form that we just picked up a minute ago is dfi dv is equal to r sub I. All right, so we didn't really change much going from a batch to a plug, or plug flow, with the exception of instead of talking about moles N, we're now talking about molar flow rates F. And the more than one reaction, the multi-reaction form, was similarly adjusted from an N to an F and a T to a V. And then finally, the packed bed reactor, if we have dxa dw, this is going to be equal to Ra prime over Fa naught. And the multi-reaction form is dFi dw is equal to r sub I prime. So the reason that I put this up here is to show you how similar this is to the stuff that you've already learned. All you need to do now is switch your interpretations of what those independent and dependent variables are. Instead of time and moles, it's now volume or weight and flow rate. We'll get to the x's here in a minute. But that's a nice summary table. We're going to add one more when we're all done, probably in 2 weeks. The fourth reactor will go down here. The reason we put that reactor fourth is because it doesn't use any of these forms, which is another reason why it can be confusing, in my opinion, to do what the book did and talk about them all at the same time, because they don't all have the same forms. So we haven't really changed the forms, we've just changed the words, or the letters, I should say. A little bit of the jargon that we have to deal with because we are dealing with flow systems. Sorry, just again to reiterate, keep that little summary table somewhere so that you have it, because those are all the differential equations that we'll need in terms of material balances for these 3 reactors. It'll never get more than that. Those are always the ones that we use. A little bit of terminology that has changed. The first one is that X sub A, like I said a moment ago, it used to be N sub A naught minus Na over Na naught. That really hasn't changed, except now we have Fs. So it's Fa naught minus Fa over Fa naught. That's it. No difference there. A few more terms that we haven't seen before. And this is where we run out of letters again. So the same way that we had too many Ks, we also have too many Vs. We have V as a volume. That's an uppercase V. We have nu, which is a stoichiometric coefficient, which looks strikingly similar to yet another V. Now we have a lowercase v. Lowercase v is a volumetric flow rate. So it's related to the capital V, except it's on a per unit time basis. Just as a terminology note, if I say capital V, that is usually volume. And right next to it, I will write the little, actually you can see it, see? This is how I write a lowercase v. I don't have a way to make it clear every time that I'm using an uppercase V and a lowercase v, except by context. If I'm talking about a flow reactor, we don't care what volume is in a flow reactor, we only care what volumetric flow rate is. So on these, a lowercase v is equal to the volumetric flow rate. So if you see one of my V's and you can't tell whether or not that V is a capital V or a lowercase v, go by the context. You'll never see a lowercase v for a batch reactor, and you'll never see an uppercase V for a flow reactor. So molar flow rate, or sorry, volumetric flow rates will look something like cubic meters per second, or liters per hour, or some sort of volume per time. There's another V that we use, which is V sub 0, which is the inlet volumetric flow rate. So the same as we would initially have a temperature or pressure, we also have an initial volumetric flow rate. The relationship between those two is something that we're going to spend most of the next lecture working out, because you can imagine we can force a batch reactor to have constant volume, right? All we have to do is put it inside a rigid container, suddenly the volume doesn't change. There's no way for us to force the volume to be constant in a flow reactor. We might be able to keep it from expanding out using the walls of the reactor, but it can always expand up and down through the distance of the reactor, or along the axis of the reactor, because there's nothing there except more gas. So the relationship between these two is something that we'll spend next class working on. A couple other parameters that you'll see occasionally in these reactors. There's a new version of T we have, which is tau. Tau is the capital volume divided by the little volume, V naught. All right, I guess I right away broke my own rule, which is that, yes, that's a capital V associated with a flow reactor. Sorry, we're limited on letters here. That's all we can do. This is called a residence time. The reason I bent the rule there is because we usually just talk about tau. We rarely talk about capital V here. This one will have units of time, so something like seconds or hours or minutes or something like that. And what this represents is the typical amount of time that some element of either the fluid or the reaction, or sorry, the reactant or the product, it doesn't really matter which one, The typical amount of time spent in the reactor. Ding. The people watching the podcast are going to have no idea why I just did. And they'll never know. Because we're just going to move on. Residence time it's actually a really powerful tool because depending on the kinetics inside there, the residence time of individual chunks can change. So we use it as a diagnostic tool to figure out what's happening inside our reactor. But at this point, all we're really worried about residence time is so that we understand the jargon. Right? If somebody says residence time, they're giving you this relationship between how big is the reactor and how fast is stuff moving through the reactor. For us, it'll always be a constant. Normally, you can get what's called a residence time distribution. So every element does not spend the same amount of time in there because the flow isn't perfectly plug flow. But for us, it is going to be perfectly plug flow. So this tau is never going to be anything except a number. Somebody will just tell you tau is 2 minutes or something like that. The other two parameters that we have, which these are specific to the phase that they're interested in. So GHSV is called a gas hourly space velocity. The gas hourly space velocity is equal to 1 over tau if you evaluate tau at standard temperature and pressure. What do I mean by that? It means, if you just write this out, the inlet volumetric flow rate evaluated at standard temperature and pressure divided by a volume. Mostly the only reason that we would use something like a gas hourly space velocity is to specify a flow rate. And to be honest, we're not going to use it very much in this class, but you need to be aware that what it is a way to specify a flow rate. So if I tell you the reactor is 1 cubic meter and the gas hourly space velocity is whatever, such and such per second, you can back out what the flow rate is under standard temperatures and pressures. There's not much else to gas hourly space velocity. And in fact, most literature doesn't really use that anymore anyway. But depending on how far back you go in time, you'll experience it. And then there's also the LHSV, which it shouldn't be surprising what this is. This is the liquid hourly space velocity, which again is a fancy way of saying what the liquid flow rate is. It's a little bit easier to define because the volumetric flow rate of a liquid divided by the volume of the reactor is the same no matter where you are. Right, liquids are incompressible, so it's less necessary to define whether or not this is the volumetric flow rate at the inlet of the reactor or at the outlet of the reactor, because they're the same thing. It is relevant in the gas hourly space velocity because this is going to change. We're going to look at that next class to figure out how that volumetric flow rate term changes as you move from one side of the reactor to another. That's enough for today. The only thing we have left is concentration, which we're going to do tomorrow anyway. So I will see you all in here Wednesday. If you have one of my reactors, please give it back. And I will see you all next class.